Okay, so what we're going to talk about today is finish up chapter 10, which is on phase diagrams. That's the last section. And that's the handout I gave you guys in class. So if you want to follow along and write notes on the handout, you can. If you want to try to sketch it out, you can. What I'll end up doing is probably a little bit of both. I have them on the lecture slides already, though. But before we get to that, what we're going to do is kind of just talk about them in general. And we've seen phase diagrams before a little bit. So we've got a phase diagram. And what this is basically it's a diagram that is temperature versus pressure, and it shows what phases are present. So it's the what phases are present. For any given temperature and pressure. And they're really useful for doing any sort of chemistry where you're either going to look at high pressure systems or extremely low pressure systems, or for instance, and I never do this, but I've always wanted to find a phase diagram for a bunch of stuff on, say, Jupiter or Saturn where the gravity is immense and the pressures are very high. And for instance, you might find that at certain depths in Jupiter that, you know, oxygen might actually be a solid or something. And so you have all sorts of different possibilities or potentials there. So it shows what phases are present. The lines on the graph represent phase changes. So anytime you cross a line on the graph, you cross or you change phases. And then there's a couple other interesting points that are on the graph that we'll talk about, but I think we'll just basically go and actually show a graph. So this should be, let's see, the graph for water. And so notice that we have the pressure in atmospheres on the y-axis, and so we go from fairly low pressures to 1. Remember, that's just our normal atmospheric pressure, so that's a good reference point. And what we'll do is we'll compare and contrast this to a phase diagram for carbon dioxide in a minute. So at very low pressures, notice that carbon dioxide or water exists as either a solid or a gas and doesn't exist in the liquid phase. And so this is the area on the graph where, for instance, sublimation can occur, or the opposite, which is deposition. And then if we kind of keep looking at the lines, this line right here that's going up and down, that's the phase boundary between solid and liquid. That's, of course, freezing. Actually, I guess I'll do it the way I wrote the arrows. So melting and freezing. And then this line over here between liquid and gas is, of course, evaporation and condensation. So this is just another way to look at all those different phase transitions. And then there's a bunch of other interesting points on the graph. For instance, if we take a look at it at 1 atmosphere right here, that's 1 atmosphere and 0 degrees Celsius, that's our normal freezing point. So that's what we're kind of used to. That's where we would normally expect things to look at. And then notice that correspondingly, if we're at 1 atmosphere, of course, the liquid gas line is at 100 degrees Celsius and 1 atmosphere. And so that's our normal boiling point. But depending upon when we change or what temperature or what the pressure is out, we can have gas boiling at lower temperatures. This portion of the curve, for instance, we've already actually seen. This is the portion that we were talking about when we had that Clausius-Clapeyron equation. And that's just, we looked at only the portion between 0 and 100 degrees and up to 1 atmosphere. We never changed those temperatures. There's a couple extra points on this graph that are interesting. For instance, the triple point is interesting simply because at that point, solid, liquid, and gas all coexist. So for instance, you look in your book, they have a picture where they show a beaker that's got solid chunks of ice in it, it's got liquid water in it, and it's also boiling all at the exact same time. And so the triple point is where all three can coexist. Notice that that occurs at very low pressures for water. And so you'll never see that like, walking outside. You'll never see all three phases coexisting. The other interesting phase that's kind of there is the critical point. And the critical point is basically the temperature beyond which a gas cannot be liquefied at any pressure, or that a liquid cannot be turned into a gas at any pressure. And so what that does is that leads to that realm of what we call a supercritical fluid. So beyond the critical point, liquids can't condense, or I'm sorry, gases can't condense to liquids, and liquids can't evaporate to gases. And so we have a separate state of matter, that of the supercritical fluid. And it's kind of interesting. I mean, if you talk about it, the idea is that the molecules are too close together to be a gas, but they're too far apart to be a liquid. There's some intermediate state between a liquid and a gas. And so it's kind of like half liquid, half gas state. And again, it's not something that we generally worry about. Notice that that's at significantly, well, not too high of temperatures, but it's at 217 atmospheres of pressure. Not something that you're going to be finding in your backyard or even in a pressure cooker on your stove or anything like that. So that basically demonstrates all the portions of it. The only other interesting thing is this little segment of line here between the triple point going up towards that. Notice that the slope of the line is negative. This turns out to be unusual, meaning it's normally sloped towards the positive side. And it's unusual because we know that water is more dense as a liquid than a solid, which is the exact opposite of what we expect from most substances. Most substances, the solid is much more dense than the liquid. Now, we're kind of lucky that for ice, solid is less dense, because that means the ice floats on the top of the lake instead of lakes freezing from the bottom up. I don't know how life would change in a lake or aquatic environments if we really froze from the bottom straight up to the top. I have a feeling it probably wouldn't work as well. Stuff couldn't shelter or weather through the winter.
And why was it?
It's because the solid is less dense than the liquid, so the solid floats up. That's ass backwards from probably 99.9% of the other compounds that we can talk about. And the reason for that is because water forms has those hydrogen bonds. And we showed you that crystal structure where it forms the hexagons, and I put that back in the display cabinet. And so what it turns out is because of that special hydrogen bonding, because it forms that hexagon structure, the solid is actually a little bit less dense than the liquid at any given time or temperature. And so it floats. Not normal though. Although we think it's normal just because, heck, we see water more often than any other liquid in existence, right? Okay, so that's a phase diagram for water. We can have the exact same phase diagram for CO2, which we know more commonly as dry ice. And notice, though, that the scaling is different on this. Whereas sort of 1 atmosphere is here in the middle of the graph for water, for CO2 it's way down here at the bottom of the graph. And so notice that, for instance, the triple point of CO2 is actually, at minus 56.4 degrees Celsius, so very cold, but it's also at 5 atmospheres of pressure. And in fact, notice this whole line that you can't have liquid water, or not liquid water, sorry, liquid CO2 below 5.1 atmospheres. And so you will never ever see CO2 liquid, at least not naturally, because it's never 5 atmospheres out, right? And so one of the things that we know about dry ice, and the reason it's called dry ice, is because it does not melt from a solid to a liquid. Instead, it sublimates. And so it goes straight from the solid to the gas phase as we increase temperature. And that's because if you look on that phase diagram, you can't even have a liquid below 5.1 atmospheres of pressure, something that we don't see on a day-to-day basis here. Also notice that the slope here is positive. That simply means that the density of the solid is greater than the density of the liquid, which is what we would say is normal for most substances. So the types of questions that you're going to be asked are, a lot of this is honestly just definitions of things, meaning, can you define what a triple point is? Can you tell me what a supercritical fluid is? Can you tell me what the critical point is? The other thing that we might ask you to do is, for instance, pick a point on the graph. So like, for instance, if we said, it's what, minus 20 degrees out today, minus 10, I don't know, someplace in there. It's minus 10 degrees Celsius. Well, that's over here, right? And again, the graph's not to scale, I don't really care. And of course, it's 1 atmosphere out generally. And so we could say something like, for instance, if we decrease the atmospheric pressure by X amount, at what value of pressure do we end up going from a solid to a gas? Or, we might say, you've got a solid at, 500 or 200 atmospheres at minus 10 degrees Celsius. If I heat that solid up to, say, 10 degrees Celsius, what phase transition occurs? And in this case, you would have to say that it goes from a solid to a liquid, so that is melting. Or we could say something like, we have liquid water at, say, 50 degrees Celsius. I lower the pressure to some value. What phase transition occurs? Well, the phase transition that occurs there is evaporation. And so basically we can draw lines all over this graph and simply ask you what occurred when I changed either the temperature or the pressure. Or conversely, it's a little harder to do because the graph doesn't have a whole lot of values on it, but we could ask, for instance, at what temperature will this phase transition occur, or at what pressure will a certain phase transition occur. So that's it for chapter 10. My take on chapter 10 really is that I almost consider it a grab bag of stuff. Meaning there's lots and lots of information in the chapter. It's kind of, starts talking about liquids, talks about solids, and then we're going to pick up that third phase of matter. So chapter 9 is going to be all about gases. And what I find interesting also is that we sort of have one chapter for liquids and solids, but we have an entire chapter just for gases. So, I don't know, one of my pet peeves about this book is the way it divides up the information in this chapter. It really is kind of spotty. So what we want to do next is start talking about chapter 9. And part of the reason we did these out of order is that chapter 10, especially the intermolecular forces, play a big role in liquids and solids, and we had just finished talking about those in chapter 7, so I figured it would be a good time to talk about them and not have too much distance between them. And so chapter 9 kind of can fit anywhere. I've actually considered doing chapter 9 before chapter 7 even. And one of the reasons that chapter 9 can be done anywhere is that we're going to see that gases are kind of unique, or at least different in them. So let's take some general properties of gases. And the idea is that we want to kind of compare and contrast those with solids and liquids. And this is really kind of a review of what we talked about in chapter 1. So the first thing we know about gases is that they are compressible. Therefore, we know that pressure has a large effect on them. And the reason they're compressible is that the atoms are far apart. And so there's a lot of empty space. If we take a look at a typical gas at, say, room temperature and pressure, then the gas is only about 0.1% of the volume. Now, if we compare that to liquids and solids, so we'll start a little column over here just for them, liquids and solids are not compressible. And the reason they're not compressible is that the atoms are close together already. And in fact, if we take a look at a typical solid or liquid, we find that it's on the order of 70% of the volume is actually the atoms themselves. So they're so close together that you really can't get them much closer together. And the other kind of part for that, or the other part that is there, it's because, for instance, for gases, we tend to ignore intermolecular forces because the kinetic energy of gases is so high that they don't interact. Whereas for liquids and solids, the intermolecular forces are very important. And compared to the kinetic energy, they're either a lot less or about equal to it. And so, for instance, the atoms in a liquid or a gas, or a solid, I'm sorry, tend to either be frozen in place, if we're talking about a solid, or if we're talking about a liquid, they flow. Whereas the atoms in a gas are moving at very high speeds and are very far apart. The last property that's kind of a result of these is that gases have an indefinite, got to spell it right, volume, and they also have an indefinite shape. What that means is that they'll expand to fill any space, and their shape, or they take the shape of whatever space they're in. Now, if we compare that to a liquid and a solid, well, solids have definite volume and they have definite shape, meaning they're basically fixed. You can't take a solid and change its shape very easily. Liquids have a definite volume, but they do have an indefinite shape, which means that they can basically flow. And so they'll fill the bottom of any container. They won't expand to fill the entire container. And perhaps so another example would be, for instance, gases are always homogeneous. Meaning they mix completely. And whereas liquids and solids can be homogeneous or heterogeneous, and quite often they do not mix at all. For instance, if you have oil and water, those two substances don't mix at all. They stay completely separate. And that's again because intermolecular forces are important for solids and liquids, and intermolecular forces are unimportant for gases, or at least they're much less important. Meaning, we're going to talk about what we call the ideal gas laws, and then we'll also talk about the corrections that we can make to factor in sort of that chemistry. Okay, so let's talk about how do we know gases exist? Meaning liquids are easy to see. But most gases are invisible or are clear or I won't say invisible, but you know, we don't actually say, oh look, I can see the oxygen over there or the nitrogen over there, meaning that you can't really see gases, you don't really feel them. Well, the easiest way that we can tell gases exist is they exert pressure. And so here we're going to get a little bit into some physics and briefly define some variables for that. So here's my lovely little balloon. And the idea is that we know that those gas molecules are zinging all around. And we've actually kind of looked at this a little bit when we looked at pressure and volume work, which sometimes I think that Chapter 8 stuff is out of order and we should talk about pressure and volume in Chapter 9 before we talk about it in Chapter 8. But basically the kinetic energy of the gas molecules exerts a pressure on a surface. And so we can write that the pressure exerted is equal to the force over the area that it's exerted on. And we measure force in newtons, and we measure area, well, basically anything we want, but meters squared is probably the best. Now, Gabe, since you really are in physics, we have to ask you, what is force really equal to? Yeah, so we can also say that it's mass times acceleration, so mass. And we measure mass in kilograms. What do we measure acceleration in? Yep. And then area still stays in meters squared. And so if we take a look at that, it gives us the units for pressure as kilograms times meters over seconds squared all over meters squared, which is really just kilograms meter second squared. Now, when's the last time you heard someone talking about pressure that used units of kilograms meters squared second squared, or kilogram meter per second squared? Unless you're in physics class. I don't know, did you use that in physics when you talked about pressure? Yeah. So we call this unit a Pascal. Has the abbreviation PA. And even then, we almost never talk about pascals because a pascal is a very, very small unit of measurement. If we take 1 penny, that exerts a force of about 250 pascals. And we're usually talking about more things than just a penny. So the typical units for pressure are generally considered the following. We usually measure it in terms of millimeters of mercury, and our sort of standard is 600 or 760 millimeters of mercury. That's equal to 760 torr. So millimeters of mercury is because this is the height of a column of mercury due to atmospheric pressure. Meaning, if we think about the fact that, you know, we're on planet Earth, so here's the Earth, and then we got some atmosphere. That looks like an atom, screw that. We'll just sketch a better picture. So here's a dish of mercury. So that's liquid mercury. And if I invert a test tube in it, so this is an evacuated test tube, then what happens is we know we have the weight of the atmosphere pushing down. And what that's going to do is it's going to cause the mercury level to rise. And it turns out that at normal atmospheric pressure at sea level, that creates a column of mercury that's 760 millimeters high. So that's where the 760 comes from. And then the torr is named for some guy named Torricelli or something like that. He was an Italian. He's the one that invented this. And so those are kind of what I would consider the common units that we use on a day-to-day basis. The other unit you're going to see is 1 atmosphere. And that's simply an arbitrary unit that's simply defined as the pressure at sea level. And then if we put that in sort of what we would call the SI units, that's 101,325 pascals. So I think one of the reasons we tend to use millimeters of mercury or atmospheres for most of our calculations is because we don't want to drag around a huge number like 101,352 pascals. Other units you'll find is pounds per square inch. And I don't know, I'm trying to think, is there one other? Oh, sometimes you'll see pressure referred to as in bars. Not bars that you go and drink at, not bars that you pry things open with, but bars that you measure pressure in, which, I don't know, that was pretty silly, I guess. One of the reasons we use mercury, and I think this is an interesting aside, so we use mercury because if we make a water barometer, it ends up creating a column of water 34 feet high. Meaning the density of mercury is much, much greater than the density of water. And so mercury makes a very small column, water makes a very large column, about 34 feet. And so if we had a barometer made out of water, in order to go test it, you'd have to run up 3 flights of stairs and look out at it, which isn't very convenient. Whereas about 760 millimeters of mercury, you know, something like this, not too bad, right? We can kind of hang that on the wall if we want. And in fact, in the old classroom, we had one hung on the wall. We never bothered hanging them in this classroom since, frankly, we're only going to be here a year, theoretically. Okay, so a manometer is great for measuring things versus atmospheric pressure, but we tend to use manometers more often. Manometers. And there's two types of manometers. We can have open versus closed ones. And there's, of course, I'm sure some lovely pictures in your book. I'm going to sketch one right here. So here's our gas. And then we have it hooked up to a valve. And then that's hooked up to a big U-shaped tube. Like that. And then the U-shaped tube is filled with mercury. And so if one end is left open, what we have pushing down on it is atmospheric pressure. And on this side, what we'd have in the tube is the pressure of the gas. And so if we measure the difference between those mercury levels, and say, for instance, it's 500 millimeters, then we can figure out the pressure of the gas. And there's two formulas that you can think of. The pressure of the gas is either going to be equal to the pressure of the atmosphere minus H, meaning the height of the mercury or the difference in the mercury column, or it's going to be atmospheric pressure plus H. And you can figure out which one to use by using some simple logic. For instance, if I've got 760 millimeters of mercury pushing down, and I'm pushing the mercury more towards the gas, then we know that here the pressure of the gas has to be less than the pressure of the mercury, or pressure of the atmosphere, sorry, not mercury. And so in this case, we know that we should simply use the subtraction formula. And so we can say that P gas is equal to 760 millimeters of mercury minus the difference, which is 500 millimeters of mercury. And we get that the atmosphere, or the pressure of the gas, is 260 millimeters of mercury. And then, of course, just to keep things, I don't know, won't say interesting, but just to mix things up, what you'll find is that any problems in the book and any problems on the homework and tests will always have funky units, meaning if it gives you the information in centimeters or millimeters of mercury, it'll ask for the answer in atmospheres. In which case, you know, you simply do conversion factors using these. Or if I give you some information in pascals, I might ask you for the answer in millimeters mercury. So one of the things you're always doing in this chapter is converting between units because, well, that's just what chemists like to make you do, little silly things like that. Okay, so that's some basics of sort of manometers and stuff. Let me just look, make sure I haven't thrown any questions on the homework that I didn't ask. Yep, lots of conversion factors. You guys should be good at those. A couple manometer questions. The last one's a little tricky, but that's okay. And you have to sketch a few of them, but I think you guys will do okay on that. So the second thing we want to talk about is the basic, or the gas laws. Or the idea is that for gases, they're based more on physical laws, not chemical laws. So again, this almost always reminds me in this section that this is more about physics than it is about chemistry. And the reason for that we say it obeys physical laws is that the molecules are far apart. The kinetic energy available to them is much, much greater than any intermolecular forces holding them together. And what that really means is that they do not interact. And so there's no chemistry. There's no chemical reactions generally going on. And so we can have what we call a physical description, in which we basically can treat the gas molecules as points or dots that don't interact. Whereas for solids and liquids or chemical laws, they're very different. Here we would need to know, for instance, the intermolecular forces to react and form bonds, etc. Now, I'm not saying that chemistry doesn't exist. It's just that if we take hydrogen and compare it to helium separate, they have the same properties, or at least the same rules describe them. The only thing that's different essentially is their mass. Whereas when we're talking about chemistry, we're saying, like, for instance, if I take H2 gas plus O2 gas, I can make H2O. So what we're going to do is we're going to describe gases using basically physical laws. And the reason we can't do that for solids is because solids aren't terribly well behaved. We have to factor in all those intermolecular forces and all the interactions that occur between the particles. Whereas in a gas, we can simply describe it using 4 variables. So there's 4 variables that we can describe a gas. At least on what I call the 0th order, meaning the most basic level. And we should all be familiar with them already. We have pressure. We just abbreviate that P. We generally measure that in millimeters of mercury or atmospheres. We have volume. We're going to give that the symbol V. And we measure volume generally in liters. We're going to have the amount, and we're going to give that the value of N, and that's simply the number of moles. We can count the atoms. We could actually use a literal number, but it's so much easier to refer to things in molar quantities, meaning that occasionally we're going to have to use Avogadro's number to talk about things. And then the last thing we talk about is temperature. And we'll use that as T. And for 99% of those laws, we want to use Kelvin, meaning we want to use the absolute temperature scale, where 0 really means that we have no motion, whereas 0 for normal temperature scale means we don't really care what things are. And there's a series of experiments that were done ages and ages and ages ago. We talked about some of these scientists before, and what they did is they simply made observations about gases, keeping some of the items constant and some of them not. So for instance, Boyle, he did an experiment where pressure and volume varied, but he kept the temperature and the number of atoms the same, or constant, I guess. And what he took home from his observations is that volume is inversely proportional to pressure. So that little alpha symbol means proportional to, and if we write 1 over something, that means that it's inversely proportional. And so what it means basically is that if volume is increasing, then pressure is decreasing, or if the pressure is increasing, then the volume has to decrease, meaning they're equal and opposite. And then if we kind of take a look at it, what that means is that if we plot pressure versus volume, we get a curve. But we can convert that into a straight line if we recognize that it's an inverse relationship, and so I should plot volume versus 1 over pressure, and then I get a nice straight line. The other thing that we can take from this is that since we can say V is proportional to 1 over P, we can replace that proportionality symbol with a constant and simply say that it's K1 all over P. So K1 is simply a constant of proportionality. And we'll talk about what that constant is and what units it has and things like that later. And then the other thing we want to realize is that, we can of course make graphs, y equals mx plus b. Well, notice that if I plot volume on the y-axis, on the x-axis I plot 1 over p, then the slope is simply equal to K1, meaning that the, meaning that the slope of this line is equal to that proportionality constant. And so we can actually measure that. And we'll talk about measuring it later. The other nice thing that Boyle's law boils down to, boy, that's kind of wrong to say, but that's okay, is that since it's a ratio like this, we can also state that P1 times V1 equals P2 times V2. Meaning, if I take a look at this and I take that equation and I simply move them on the same side, volume times pressure equals K1, well, that means that if I've got two different, volume times pressure, not two V's. If I've got two different sets of conditions, well, they're equal to the same value. And so if I have a set of data for volume 1 and pressure 1, and I have a set of data for volume 2 and pressure 2, since that constant is the same, since they always multiply together to give the same value, then we can simply say P1 V1 equals P2 V2. And so what that means is that we can set up all sorts of situations, like, for instance, for a given gas, for a gas, P1 equals 700, well, for a gas at 726 millimeters of mercury has a volume of 746 milliliters. If the volume is decreased to 154 milliliters, what is the pressure? And so we can simply use P1 V1 equals P2 V2 to solve for that. Realize that at 726 it was 746 milliliters, so I can say 726 millimeters of mercury times 746 milliliters is simply equal to the second pressure times that 154 milliliters. Solve for P, and you get pressure is equal to 4,460 millimeters of mercury. So because gases are well behaved, if we know the pressure and volume at any one point, we can figure out the pressure and volume at any other point. Now we should also point out that, remember, at constant T and N. And what we're going to find is that we're going to have a series of situations where we have a series of laws relating different variables and keeping, the other variables constant. And at the very end, what we're going to do is we're simply going to sum it up into one law called the ideal gas law. But initially, these experiments were done by individual scientists. They may or may not have known each other or communicated. And it wasn't until Avogadro, you guys remember him? He gets his own constant, so he's famous. Avogadro put it all together kind of into one equation. I think he was the one. It's either that or Boyle. I forget. I'll have to read my notes again. So the other thing that is kind of, we always love for gas laws is simply piston problems. So if I say, for instance, that this volume equals 500 milliliters and I've got a pressure equal to 250 millimeters of mercury, what happens to the piston if I double the pressure? Where is the piston? Or simply put, does the piston move up or down? Or arguably, depending upon what we're doing, it might not change at all. So what should happen to this piston? Well, we can actually do the problem if we really want. We can say that, we've got P1 V1 equals P2 V2. So if this is 250 times 500 equals, now I doubled the pressure, so that means my pressure goes to 500 times x. Well, I picked a nice easy problem. We just get that x is equal to, and I guess really I should say V2. That way we remember what we're talking about, is simply equal to 250 millimeters of mercury. Meaning that my piston should go down. Or the idea is that if I double the pressure, I have the volume. That's what it means to be basically inversely proportional. So that's Boyle's law. Now, in some cases, we actually go through and we measure these and do that. But since this is the last chapter, since we won't have enough time to get done with everything, we're not going to have a lab on this. And so we're just going to kind of take these on faith. The next one is called Charles' law. And what he did is he kept volume and temperature were allowed to vary. And he kept N and P the same. So basically we're at constant pressure, but variable volume and temperature. And what he discovered is that volume is directly proportional to temperature. Meaning if I increase the volume, that means I increase the temperature. And if I decrease the volume, that means I decrease the temperature. And again, what we can do is the exact same things we kind of did for Boyle's law, in that we can simply write that as a direct relationship and simply say that V equals K times T, or you can also write V over T equals K. And we're going to call this proportionality constant K2. And so we can make the equation V1 all over T1 equals V2 all over T2. And that's probably, again, the most common situation. All we simply do is take a look at two different sets of conditions, and if we know one set of conditions, we can calculate the volume or the temperature at any other given set of conditions, assuming pressure and the number of atoms stays constant. We can also, if we write this equation, V equals K2 times T, recognize that if we plot Y equals mx plus B, means that in this case, to get a straight line, I just have to plot volume versus temperature, and I get a straight line. And one of the things that we find is that that straight line always extrapolates to 0 Kelvin, meaning that all gases eventually have zero volume at absolute zero. Now, that's not 100% true, because we know that at some point all gases condense down to a liquid or a solid and they don't have zero volume. But one of the things I found interesting is when you read through this is that one of the ways they kind of verified absolute zero, or at least came up with that concept initially, is simply by looking at a number of gases and realizing that every single gas, despite no matter what, always extrapolated back to that specific point. So we can also have little problems, like I said, for the other ones. If I have, if at 398.15 Kelvin, a gas has a volume of 3.20 liters, what is the volume or what is the temperature if the volume changes to 1.54 liters? And so again, we just do the, we phrased it this way, V1 all over T1 equals V2 all over T2. So if we plug that information in, we know 3.20 liters all over 398.15 Kelvin is going to be equal to 1.54 liters all over T2. And of course, you guys should be perfectly capable of solving for T2 and getting 192 Kelvin. And it makes sense. If this decreases, then we expect the temperature to decrease, meaning they're directly proportional. And I think we're out of time, so we'll stop there. We'll come up with Avogadro's law in a little bit. What I would say is that homework 10, now I forgot what number it was. I think it's E, whatever one is the last one, is due on Thursday. Today's Wednesday, due on Friday. And you can also have homework 9A due on Friday, meaning we've covered enough information. And you should be able to start on homework 9B, but we probably can't finish it unless you kind of read some stuff up in the book, which honestly isn't that incredibly hard to do. So tomorrow is Thursday, and again, we're not having a lab, so wear whatever clothing you want. You don't have to dress up anything special for it. And we will continue our lecture in Chapter 9. My goal is hopefully to finish Chapter 9. I doubt I'll finish it by Friday. It's possible, I guess. It depends on how fast I talk and how quickly we go. Then what we can do is we'll have a test probably Wednesday or Thursday of next week, and we'll spend a good day or two reviewing for the final, since, well, the final is 2 parts. It's cumulative.